Welcome to the lecture number 15 of the course Discrete-time Markup chains and Poisson processes. Recall that in the last lecture we have talked about what is called number of visits. We denoted it by Vi, and then we have seen what is the distribution of Vi, and finally we have seen a very critical result which can be used to classify a state into recurrent or transient, which is basically in terms of PIIN. It basically says that I is recurrent if and only if summation IIN n runs from 0 to infinity is equals to infinity. Okay? We have seen this result that I is recurrent if and only if summation PIIN is equals to infinity, where the sum runs from 0 to infinity, and we have seen I is transient if and only if summation n equals to 0 to infinity PIIN is less than infinity. Okay? These two very important result we have seen, and then today we will going to discuss about what is called class property. Okay? So, we are going to basically first show that transient or recurrence are class property. Before going into this one, just recall that what is a communicating class. So, we just recall that if this is our state space S, then if I take all the, if I consider the relation that I and J are communicating each other, that means J is accessible from I and I is accessible from J, and in layman's term that basically mean that in some step with positive probability I can move from I to J, and similarly in some step with positive probability I can move from J to I. Okay? So, we have seen the definition was that there exist n and m integers such that P I to j, I can move from I to j in n steps. So, this probability is strictly greater than 0. Similarly, from j to I in m step is strictly greater than 0. And we have seen that if I talk about this relation, then this relation actually partition the state space. Okay? The relation actually partitions the state space, and all state here communicates, all state here communicates, similarly it communicates here and it communicates here, and no state from one partition to another partition communicates. I can move from this to this, but I cannot, in that case I cannot come back from here to here. Okay? So, moving out is possible, but in this case moving in is not possible. If moving out and moving in is possible, then this completely is a one class. Okay? So, that is why basically this way we partition, and now we look into the theorem. This theorem basically tells us that, well, C be a communicating class. Suppose C be a communicating class, suppose C is this set which is a communicating class, then either all states in C are recurrent or all are transient. So, in C, if either all of the states in C, suppose C has several states, all of the states in C either recurrent, all of them will be recurrent, or all of them will be transient. There cannot be any communicating class in which one state is recurrent and another state is transient. That cannot happen. Only possibility is that in a communicating class all the states are of the same type, either they are all recurrent or they are all transient, and that's why this particular property is called class property. That basically mean that in a class that all the states are either transient or recurrent. Okay? All of them will be transient or all of them will be recurrent. It is like that. Okay? So, let us move into the proof, and to prove this one, basically we are going to use the definition of communication, as well as we will use the Chapman-Kolmogorov equation, and we also going to use what we have seen in the last class, that means these two things that we are going to use. Okay? So, let us proceed to the proof. So, C is a communicating class. So, I take two two states in C. So, if this is my S, inside that I have C, and suppose I and J are two communicating class here. Okay, I and J are two communicating class here, and I and J are two different states. Okay, I and J are two different states. Then by definition of the communication, we know that there exists a n and m greater than equals to 0, such that Pijn is greater than 0 and Pjim is greater than 0. So, that means from I, if this is I, this is J, from I can move to J with positive probability in n steps, and from J we can move to I with positive probability in m steps. Now, suppose that I is transient, suppose that this I is transient, we want to show that J is transient. Okay, we want to show that J is transient. If we can show that J is transient, then I am done, because here I am taken any pair of states is Ij in C. So, any pair of state, if one of them is transient, then other is transient. That means all the states in C will be transient. Okay, I take any pair of state, if one is transient, then other is transient. If I can able to prove that, then that basically mean that all the states in the communicating class C will be transient. Okay, so we assume that I is transient, we want to show that J is also transient. So, how can we prove? How can we proceed? The way of proceeding is simple. Just recall that Chapman-Kolmogorov equation. So, Chapman-Kolmogorov equation basically tells us that if I want to find out Pij n plus m, that I can write at summation k belongs to S, P I to k in n step and P k to j in m step. Okay, that's why I can able to write. So, that basically the idea is nothing but if this is the state I, this is the state j, I want to move from here to here in m plus n step. I want to find out the probability of moving from this to this in m plus n step. Then what I am doing, I am taking a intermediate state k, such that I am moving from here to here in n step and here to here in m step, and then I am taking this k can take any values in the state space S. That is the idea. So, the path I am considering here passes through k, and I reach from I to k in n step, and then I just move the k over all the possible state in S. That means basically the path actually moving to all possible values of k in between, and from I to k I am going in n step, and then k to j in m step. Okay, that is the idea. So, here I have a sum. Now, notice that if I take a particular value of k here, suppose I take k equals to k naught, which of course belongs to the state space S, then I can write Pij n plus m is actually greater than or equals to Pi k naught n P k naught j m. Okay. So, what basically mean? That means I am taking one of the sum from here, a special value of k naught here, k here. So, one of the component from here, not the whole sum, and because this product is always greater than equals to 0, because they are the product of two probabilities. So, they are always greater than equals to 0. So, if I take a particular term, that will be even smaller than this sum, So, I have this particular inequality. Okay, and the way to interpret it physically means that I am moving from I to j in a n plus m step, but I am taking only one path, which is taking me through the state k naught, Okay. So, there could be any other several possibility there, that I move to n and m, maybe some other k1 here, I move to k2 here in n and m in this side. So, I am just removing all these possibilities, I am taking only one possibility, and that means that probability will be lower. Okay, I am taking only one path, which actually leads me to j from I through k naught at the ns step. Okay, at the ns step, and instead of taking all the possible k, I am taking one. So, this will going to happen. Okay. So in the similar manner, if I have something like that, I am from I come back to I in m plus r plus n step. Okay, in n plus r plus m step I want to come back. That probability is this. Now this can happen in several ways. One of the way is that from I move to j in n step, then from j I move to j in r step, and then for j I move to I in m step. Okay, that can happen. Now this, for any value of j, this can happen. Okay, in any value of j this can be written, but I have taken a particular value of j, which j I have taken here. So that's why again using the similar thing, that this will be that instead of taking all the paths that leads me to I in n plus r plus m step, I am taking one particular path which is taking I to j in n step, j to j in r step, and j to I in m step. So that means that this probability that moving from I to I in n plus r plus m steps is greater than or equals to moving from I to j in n step, j to j in r step, and j to I in m step. Okay, so this why I get this particular inequality, and this inequality is hold true for any value of r greater than equals to 0. For any value of r greater than equals to 0, this inequality hold true. Now you see that we have that this quantity is strictly greater than 0, this quantity is strictly greater than 0. So this one is greater than 0, similarly this one is greater than 0. So that means that now I can able to write that Pij r, I can able to write that Pjr, which is basically this quantity, is less than or equals to Pii n plus r plus m divided by Pij n Pji m. Note that in this case this n and m I have fixed earlier that m and n I am taking for which this quantity is strictly greater than 0 and this quantity is strictly greater than 0. So m and n are fixed earlier through this condition. Then I am just taking r, which can take any value greater than equals to 0, and I have this particular inequality. Okay. Now let us take the sum on both sides. So sum over r equals to 0 to infinity this side, sum over r 0 to infinity on the other side. Okay. So both side I take the summation with respect to r, and when I take that I get actually this one, that Pjr taking the sum over r equals to 0 to infinity is less than or equals to these two quantities does not depend on r. So I take them outside of the summation sign, and finally I have summation summation Pii n plus r plus m, summation Pii n plus r plus m. Okay. Now we have assumed that I is transient. So I is transient basically mean that I transient, that if and only if summation Pii in n step is less than infinity when I am taking the summation n equals to 0 to infinity. Now look into this sum. This sum is basically Pii n plus m. If I take r equals to 0, then Pii n plus m plus 1 plus so on so forth, it is going on. Okay. And this sum is basically nothing but Pii 0 plus Pii 1 and so on, it move on. Somewhere I will have I n plus m plus Pii n plus m plus 1 and so on so forth. Okay, and so on so forth. So clearly if this sum is finite, now if I take only this part, this part sum has to be finite, because with this part when I am adding something non-negative, even I am getting finite. So if I remove this part, the rest of the part has to be finite. So here this part is finite and these two quantity are strictly greater than 0. So if I divide the finite quantity by a positive constant, then that will automatically will be a finite quantity. Okay, so we finally proved that summation r equals to 0 to infinity p I j j r is finite, and this implies that j is transient. Okay, this implies that j is transient, and we are done with the proof. We start with I is transient, we prove that j is transient. We are done, and to prove this one, what we have used the definition of communication, we have used the Chapman Kolmogorov equations, and from that I derived this inequality, and finally we have used the necessary and sufficient condition for transient and recurrent. Okay, the necessary and sufficient condition for transient we have used. So that means that one side we have shown that if I is transient, j is also transient. Now I have to show the other one, that if I is recurrent, then j is also recurrent. So let us move to this one, and that proof is quite simple. So now suppose that I is recurrent and we want to show that j is also recurrent. Okay, if I am able to show that, I am done, because in a communicating class, is one state is transient, we have shown that the other state is transient. So that means if one of them is transient, all others are transient. On the other hand, now we are going to show that if in a pair one of them is recurrent, then the other is also recurrent. That means if one of the state in the communicating class is recurrent, then all of the rest of the state in the communicating class has to be recurrent. There is no other option. Okay, so let us proceed in this way. Let us prove this one by contradiction. If possible, suppose that j is transient. Okay, I want to show that j is recurrent. So suppose, if it is possible, if it is at all possible, suppose that j is transient. And finally what I am going to show, we are going to show that if we assume that j is transient, then there is a contradiction. So if there is a contradiction, that means what I am assuming that is false, and that means this statement is false, and j is not transient, that means j is recurrent, because a state is either transient or recurrent. So j is not transient means that j is recurrent. That is the way to prove. Now let us find this contradiction, where we get the contradiction. So j is transient and I and j both belongs to a communicating class. So I and j communicates. Okay, and because basically that we have pointed out that communication relation is basically a reflexive one. So I j communicates means j I also communicates. Okay, so j and I communicates, j is transient, that means I has to be transient, but our main hypothesis is that I is recurrent. So clearly this is a contradiction. So j cannot be a transient, so j is a recurrent state, and that completes the proof. Okay, so the first part, when I is transient, j is, to show that j is transient, we have used several concepts, but when basically we try to show I is recurrent, we want to show that j is also recurrent. By contradiction, very easily we prove that, we can prove that once we prove this part, okay. So that completes the proof that for a Markov chain, if I have a communicating class C, then inside states, all of them will be either transient or all of them will be recurrent. Okay, all of them will be either transient or all of them will be recurrent. That is the scenario inside a communicating class, and that's why we have given some name to them. For example, a communicating class is called recurrent class if all the states of the class are recurrent. Okay, so we know that all the state, if one of them are recurrent, all the state are, so in a communicating class all the states are either recurrent or transient. If the classes are recurrent, if the states are recurrent, then we say that this communicating class as a recurrent class. If the states are transient, we call that is a transient class. Okay. So, if all the states in a communicating class are recurrent, we call this is a recurrent class. If all the states in a communicating class are transient, we call it is a transient class. Okay. Similarly, we do it for Markov chain also. If a Markov chain is irreducible, recall the definition of the irreducibility. Irreducibility basically means that all the states of the Markov chain communicates among themselves. So, there is only one communicating class which is basically the state space. Okay. So, in case of irreducible Markov chain, it basically means that all the states of the Markov chain communicates among themselves. So, that means that there is only one communicating class, and that one communicating class is nothing but the state space. So, now for a irreducible Markov chain, that means that all the states will be either recurrent or all the states will be transient. Okay. Either all the state will be recurrent or all the state will be transient for a irreducible Markov chain, because there is only one class, and as we have seen that in a class, in a communicating class, either all the states are recurrent or all the states are transient. So, in case of a irreducible Markov chain, all the states are either recurrent or all the states are transient. Okay. All the states are either recurrent or all the states are transient, and that's why we sometimes calls that the Markov chain is recurrent if the Markov chain is irreducible and all the states are recurrent, or we say that Markov chain is transient, that basically mean that Markov chain is irreducible and all the states are transient. Okay. So, these two terminologies we are going to use, that a class is recurrent means all the states inside the class are recurrent, and a Markov chain is recurrent, that basically mean that Markov chain is first irreducible and then all the states are recurrent states. With that, let us proceed and let us now see another theorem which basically helps us to tell whether a state is transient or recurrent. Okay. So, this says that every recurrent class is closed. So, what does mean? What does closed mean? Just recall that closed basically mean that if I have a class C, then closed basically mean that I cannot come out of the class. I will be inside the class always and I cannot come out of the class. Okay. So, that means that if I have I here, I have some j outside C, then basically j is not accessible from I. J is not accessible from I. Okay. That basically mean that from I cannot go to j for all j does not belongs to C and for all I belongs to C. Okay. For all I belongs to C and all j does not belongs to C, I cannot go from I to j. That basically means the closed class, and that basically mean that from the class I cannot go outside. Okay. So, what we are going to prove now is that recurrent class is always closed. Okay. So, if I have a communicating class whose all the members, all the states inside that communicating class are recurrent, then we call the corresponding class is a recurrent class, and this result says that such classes are closed. So, from such class, if I start from such class, I have to be in that class forever. I cannot go outside that class in future. Okay. Or if I come to this class from outside, if I come to this class, that is of course possible. From outside I can come to this class. Once I come to this class, I am completely, I will be absorbed in this class. I cannot come out of this class again. Okay. I have to be in this class forever. Okay. So, let us proceed. So, suppose that C is recurrent class. Okay. C is recurrent class, that is the hypothesis given in the theorem, and suppose now I assume that C is not closed. I assume that C is not closed. What does this mean? That means that if I belongs to C, I am in C, and J does not belongs to C, I am outside C, then I can move from I to J in some finite time. So, is not closed, that means that from I belongs to C and J does not belongs to C, I can go from I to J. For some I belongs to C and some J does not belongs to C, I can move from I to J. That is the not closed. Closed mean I cannot go outside this state, outside this class, and not closed mean that I can actually go outside this class. Okay. So, from I can move to J for some I in C and some J does not belongs to C. Okay, and so that basically mean that from I to j I can go, that basically mean that p I j in some k step is greater than 0. This is nothing but p I j k in some k step I can go outside. So this is can be done in k step at least. Okay, so that means that probability has to be strictly greater than 0. Okay, now look into this. So now we are going to show that under all these conditions this one going to be true. Why? The reason being that, see, the first one is nothing but I am starting from I, and first one is nothing but at the k step I am in j. Okay, so that means that I start from 0, I have time k here. Suppose this is the state I, this is the state j, I belongs to C, j does not belongs to C. Now I am starting from I, and at the time k I am at j. Okay, so it moves like that, and finally at the time k it reaches there. Okay, now what is this mean? This mean that xn equals to I for infinitely many n. Okay, and xn equals to I for infinitely many n's. Notice that this is intersection. So I just move like that, and I finally reach here. Notice that I can cut that, I can reach I for several times, and from here again it move on like this, it again come back to I again and again. Okay, I am talking about this. Now what does this mean? Notice that this is j. Okay, what does this mean? This means that from j I can actually go to I. There is a positive probability from j I can come back to I. So that means that if this happens, then if this probability is greater than 0, if this probability is greater than 0, that basically mean that from j I can go to I. Okay, because this is j, and then I at the k step I am in j, from starting from I at the k step I am in j, and then if xn equals to I, if I have to visit the state I for infinitely many times, that means I have to, from j I have to again come back to I. There is no other possibility. So that means from I can go to j, and from j I can go to I. From I can go to j, and if this probability has to be strictly greater than 0, then this has to be from j I can go to I. So that means now if I club this one with this one, that basically mean that I and j communicates. Okay, that basically mean that I and j communicates, and that cannot happen because I have taken that j is not in C. J is not in C, and if I and j communicates, then j has to be belongs to into the class C. Okay, then j has to be belongs to the class C. So this cannot happen. So that means this cannot happen. So only possibility is that this probability is equals to 0. Okay, so I hope this expression is fine with everyone, that this probability is 0. We can show by contradiction that if possible, suppose this probability is strictly greater than 0, and if this probability is strictly greater than 0, then I is accessible from j, and beforehand I have j is accessible from I. So that means I and j communicates, and that cannot happen because j does not belongs to C, and C is the communicating class. So that means basically if ij communicates, then j has to be belongs to into the C, and but we have assumed that j is not in C, so this cannot happen. So that means this cannot happen, that means this cannot happen, that means this cannot happen. So only possibility is that this probability is equals to 0. Okay, so we have, with these all assumptions, we show that this probability is equals to 0, and now you see that it implies that this probability equals to 0 implies that this quantity is strictly less than 1. Why? Again by contradiction we will prove. Suppose if possible this quantity equals to 1. Suppose if possible this quantity equals to 1. Now let us call this is A, this is set B, then here I have probability that A intersection B. Okay, and here I have that it is basically nothing but, if possible, suppose this probability is 1, that basically mean that probability of B equals to 1. okay, and we know that if probability of B 1, then probability of A intersection B is same as probability of A, okay. If probability of A B equals to 1, then probability of A intersection B equals to A, probability of A. So that means if possible, if I assume this probability is equals to 1, this actually implies this. This actually implies this, and so if this probability is 1, that means this probability has to be same as starting from I xk equals to j, which is basically p I from I to j in k step, okay. So if this probability is 1, that means basically this probability is same as p I j in k step, okay. P probability of moving from I to j in k step, that is basically this probability will be if this probability is 1. And here we have pointed out that this probability is strictly greater than 0. So, but here we have already pointed out this is 0. So, this cannot happen, this cannot happen because we have already shown this is 0. So, this is a contradiction, and this contradiction has come because of this assumption. So, this assumption is also not true, and that implies that this probability has to be less than 1, strictly less than 1, there is no other option, okay. So now we are done, because we know that if I is recurrent if and only if this probability is 1. So this probability is strictly less than 1, that means that I is not recurrent, okay. So this probability strictly less than 1 means that I is not recurrent, because we know that I is recurrent if and only if this probability is exactly equals to 1, okay. So it shows that I is not recurrent. I is not recurrent means that I is transient, because a class has to be either recurrent or transient. So I is not recurrent, so that basically mean that I is transient, and that basically mean that the class C is transient, because I belongs to C. If C is transient, all the states in C has to be transient. So C will be transient class, and that is again a contradiction to the fact that I have assumed that C is a recurrent class here. So that means that if I assume that C is recurrent class, I start with the hypothesis recurrent class, and then if I assume that C is not closed, then that cannot happen, because here if I assume that C is not closed, I finally come with the fact that C is not recurrent class. C is not recurrent class, so C is transient class, and that is a contradiction to the fact of the basic assumption of the theorem, and so that's why basically C is not closed is false. So C is closed is true, okay. So we have proved that theorem that every recurrent class is closed. We have proved the theorem that every recurrent class is closed, okay. So what we have still now proved, first we have proved that in a communicating class all the states will be recurrent or all the state will be transient. If I have a recurrent class, the recurrent class is closed. That basically mean that if I am in the recurrent class once, I cannot come out of that particular class forever. I will be inside that particular class forever, so I cannot come out of the particular class in future, okay. So with that, let us proceed, and now let us talk about finite a kind of a partial converse of the previous theorem. So previous theorem says that every recurrent class is closed, okay. So previous theorem says that recurrent class is closed, okay. That's what the previous theorem says. Now natural question is that is the closed class is recurrent. So question is that, now the question is that is a closed class is recurrent, is closed class recurrent, okay. That is the question, and this answers partially. It basically says that not all closed class, but if the class is finite, if the closed class is finite, then it is recurrent, okay. Every finite closed class is recurrent. It basically says that. So it's not completely answered this question that is closed class recurrent. It completely do not answer this question, but partially it answers this question that, well, if the closed class is finite, then it has to be recurrent, okay. So every finite closed class is recurrent, which is the main point of this theorem, and let us now move to the proof of the theorem. So, proof goes like this. Suppose C is closed, okay, and finite. So, C is closed and finite, that is the hypothesis that I am taking, which is the hypothesis given in the theorem. And suppose the Markov chain is starting from C. So, that means I am already in C, okay, I entered into the C, the chain entered into the C. So, I am basically instead of that I am supposing that I am starting in C. So, C is here, I am already, the x naught is inside, somewhere x naught is there. Now, then for some I belongs to C, some I here in the C, we must have the following, we must have this particular thing. Why this is true? What this is saying? It is saying that starting from I, or no, not starting from anywhere, I will visit the state I for infinitely many n. Why this is true? Okay, let us think in this way. Suppose that the class is finite, okay, C is finite. So, let us take C has k members, okay, let us take C as k members, and suppose the chain can visit the first state n1 times, second state n2 times, and in the way kth step nk times. So, suppose that first state is visited n1 times, second state is visited n2 times, kth state is visited nk times. So, suppose that ith state, state I is visited ni times, okay, and of course, these are all finite quantities. So, now suppose if I take the sum of all those things, if I call n equals to n1 plus n2 plus so on so forth nk, then that means basically chain will be here for capital N number of time. What will happen n plus 1th time? Notice that C is a closed class. So, I cannot come out of the C, and at the n plus 1 time it will be not in any of these states. So, that cannot happen, clearly that cannot happen. So, at n plus 1 step, if I assume that state I is visited only n1 times, state 2 is visited only n2 times, state k is visited only nk times, then if I take capital N is the sum of all values, then what will happen at the time n plus 1? Notice that at the n plus 1, the chain will not be in any of these states. So, clearly the chain has to be go outside this state, and that is not possible because this is finite. Okay. So, that means at least one of the state here has to visit infinitely many times. At least one of the states here need to be visited infinitely many times. And that basically given here that starting from any state does not matter from where I start, at least one of the state has to be visited infinitely many times with positive probability. Okay. So, there exists a state in I in C such that the state I will be visited infinitely many times, does not matter from where I start. Okay. So, that means that probability that xn equals to I for infinitely many n has to be greater than 0. Now, let us use the strong Markup property and let us do the conditioning with respect to ti less than infinity. If I do the conditioning with respect to ti less than infinity, then we get this one. So, we can write from here that it is nothing but probability that xn equals to I for infinitely many n given ti less than infinity multiplied by probability that ti less than infinity. Okay. So, probability ti less than infinity, that means that for some n I will visit the state I. So, this one is written here, this one is written here. Now, here using the strong Markup property, it basically means that once I am in I, that the next part is this is ti, this is basically does not depend on in this part, and it is only that I start from I. So, now I start from I visit the state I for infinitely many time. Start from I visit the state I for infinitely many time. So, this probability is same as this part of the probability. Okay, so this is basically this probability, this part is this probability. So finally I have that 0 is strictly less than this probability, which is same as product of two probabilities. Product of two probabilities. So this product of two probabilities is strictly greater than 0 because of this. So both the probability has to be strictly greater than 0. Okay, so that means this specifically the second part has to be strictly greater than 0. So that means that I is not transient, because just recall that if I is transient, we have that I is transient if and only if this probability is exactly equals to 0. Okay, I is transient if and only if this probability is exactly equals to 0. So that means this probability is strictly greater than 0. That means I is not transient. So I is recurrent. And I is recurrent means that that one state in C is recurrent, so all the state in C has to be recurrent. So C is a recurrent class. Okay, so we have shown that finite closed classes are recurrent. Okay, so every finite closed class is recurrent. So we have basically in this particular lecture till now we have shown basically three very important theorems. First one is that saying that in a communicating class either all states are recurrent or all states are transient. Second one says that every recurrent class is closed. Third one basically gives us a partial converse of the previous theorem, which so the third theorem basically tells us that every closed finite class is recurrent. Okay, every closed finite class is recurrent. So the question is still open that whether if I have an infinite closed class, is infinite closed class always recurrent? So this question, the answer of these questions we will see as we proceed in the course, but still now we have just answered it partially. Now let us move on to some examples. So this example is basically a example which we have discussed in lecture number 8, and this is the basically example 14 of the lecture number 8. Just go back and check. I have just only given the diagram here. So from this diagram we have pointed out the fact that this is a irreducible Markov chain. That means all the state communicates among themselves and there is only one communicating class which is 0, 1, 2. So that whole S is basically in this case the communicating class, and this is a irreducible Markov chain. That's what we have discussed in the lecture number 8. Okay, now notice that this is a closed class, of course, because this is S, there is no point of going outside S, all the state inside the S. So this is of course a closed class, there is no problem with that. Moreover, this is a finite class because I have only 3 members in the class. So this is a finite class, this is a closed class, and now using the previous theorem that every finite closed class is recurrent, I can tell that this class is basically a recurrent class. I can tell that this class is basically a recurrent class, and that says that this Markov chain is basically a recurrent Markov chain. Okay, this Markov chain is a recurrent Markov chain. So how we deduct that the state I is recurrent? The way of deducting this one in this case is that, well, I have that S is basically the communicating class here is S, consists of 0, 1, 2. This is a closed class, this is a finite class, and now using the previous theorem we know that every finite closed class is recurrent. So this class has to be recurrent, and this class recurrent basically mean that each of its member are recurrent. So this means that 0 is recurrent, 1 is recurrent, 2 is recurrent, and the class itself is also recurrent. Okay, so that this example actually can be generalized to the fact that for a irreducible finite state space Markov chain, for irreducible finite state space Markov chain, of course in this case I have only one class. Markov chain, all the states are recurrent. Okay, so it is nothing matter that if I can have multiple, if I have maybe k states, total k states, that if it is recurrent, if they are communicating each other, that means it is a irreducible Markov chain. Using the same argument, I can able to prove that all the states are recurrent. So there is only one class in case of a irreducible finite state space Markov chain, and this is a closed class, this is a finite class. So that means that all the states of that particular Markov chain has to be recurrent. Okay. So let us move on to the next example. Again, this example was discussed in lecture 8, example number 15. So this was the diagram, and in this case we have shown that in this case 0 and 1 communicates, 2 does not communicate with others, 3 does not communicate with others. So I have 3 communicating classes in this case. 0 1 first one consists of 0 1, second one consists of 2 only, and third one consists of 3 only. In this case, all the communicating classes are finite. Okay, all of them are finite, and we have also pointed out this one, that this one and this one, these two are closed. These two are closed. Okay, we have pointed out these two are closed. So these two are closed and finite, and that says that the classes these and these are recurrent. So that means that 0 is recurrent, 1 is recurrent, 3 is recurrent. Okay, because these two are closed class, 0, 1 and 3, that these two are closed class, these two are finite class. So that means that these two classes are recurrent. That means 0, 1 and 2, these and these are recurrent classes. On the other hand, 2 is not closed. If 2 is not closed, I can deduct that 2 is transient. Why? The reason is that if possible, suppose 2 is recurrent. Okay, if 2 is recurrent, then I can use that this theorem which says that every recurrent class is closed. So this means that this implies that 2 has to be closed. 2 has to be closed, and that is the contradiction. This is the contradiction which is a contradiction, which is a contradiction to the fact that 2 is not closed. And you can see that from 2 I can go to 1, or I can go to 0, I can go to 1, I can go to 2, 3. So 2 is not closed. Okay, 2 is not closed. So this is a contradiction, which is a contradiction, and that basically tells me that this assumption is not correct. So that means 2 is not recurrent. So 2 has to be transient. Okay, so in this case we have shown that this is a recurrent class, this is a recurrent class, this is a recurrent state, this is a recurrent state, this is a recurrent state, but this one is a transient state. Okay, this one is a transient state. Let us proceed. Again, same kind of example. In this case also we have shown that there are 3 communicating classes. Each communicating classes are transient, are finite. Each communicating classes are finite. We have also showed that 4, 5, this one is basically closed and finite, of course. So that means that this class is recurrent. On the other hand, 0, 1, this class and this class, they are not closed, so they will be transient. Just like the previous example, they are transient. So here basically we have 0, 1, 2, this is a class, this one is a class, this class is recurrent class, this class is transient class, this class is also transient class. Okay. So these all the examples till now we have talked about these 3 examples, I feel. Yeah, 3 examples we have talked about some finite state Markov chain. Let us take one example where we have infinite state Markov chain. Okay. So it is basically birth-death process. Again, we have discussed it in the lecture number 10, example number 19. So in this case we have pointed out that we have 2 communicating classes. One is 0 only, and the others are basically consist of all the rest of the classes. So there are 2 communicating classes. One is 0 and other is 1, 2, 3, 4, so on so forth. Everything is here. Okay. So in this case 0 is closed, because once I am in 0, I will be in 0, because this is observing class, observing state. So 0 is closed, 0 is only one member is there in this class, so that means this is finite. So this is a finite and closed class. So that means that this 0 is a recurrent, 0 state 0 is recurrent, and class consists of 0 only is a recurrent class. Now what about this part? This part is not closed, this part is not closed. Why? Because I have a probability, positive probability from moving from 1 to 0. Moving from 1 to 0, so this part is not closed, and if this is not closed, clearly this is a transient class. Okay, this is a transient class. This is not closed, so definitely this has to be a transient class. Okay, so in this case, this one is recurrent and this one is transient. With this example, I stop here. Thank you for listening.